You got it. I will begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Pray you be with us today. Help us to just glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. Okay, so today we are talking about eigenvectors. And the problem of diagonalization. All right, so these two topics are very, very much related. I'll start with the definition of what's an eigenvector. All right, so definition. If we have a linear transformation T from V to V, so a linear transformation on vector space V over a field F, all right, then V not equals to 0 is an eigenvector with eigenvalue lambda in F provided that T of V is equal to lambda times V. All right. Let me just say from the outset that is equivalent to saying that T minus lambda times the identity on V acting on V is equal to 0. Right? So I will sometimes take T of V equal to lambda V as the definition. I will sometimes take that T minus lambda times the identity operator. When that acts on V, it gives you 0 to be the definition. Whichever you take as primary, the fact of the matter is that the eigenvector must be non-zero and a vector that satisfies this rather particular condition with respect to the linear transformation. Likewise, if we have A in n by n matrices over the field, then if V is not equal to 0 in n vectors has, A minus lambda times the identity matrix times V equals to 0 for some lambda in the field, then likewise with V not equal to 0 in Fn such that, sorry guys, words, such that that equal to 0 for some lambda in F implies V is eigenvector with eigenvalue lambda with respect to A. So we can either talk about the eigenvector of a linear transformation, or we can talk about the eigenvector of a matrix. All right? Let's see here. So, furthermore, let's get these definitions out of the way. If beta, and I really should say, eigenvector, there's an important little, both of these up here, to be more precise, I should say, with respect to T, eigenvalue, with respect to T. Now, we don't always put that with respect to T in there because, like I've put with respect to A down here. When the context is clear, I won't say what it's an eigenvalue with, or an eigenvector with respect to, but to be most pedantic, I really should say with respect to the transformation or with respect to the matrix, because the eigenvalue and the eigenvector concern our specific choice of transformation or matrix. Okay, that said, if beta equal to, say, v1 dot vn is basis for v where v1 dot vn are eigenvectors of t, which is a linear transformation from v to v. Let me just say v, which is an element of the linear transformations from v to v, right? Then beta is an eigenbasis of t, well, of v, rather, with respect to t. You're like, could I please have another definition? I really could use another definition at this point. Well, yes, I can give you one more definition. Finally, we'll use the following notation. We'll say E sub lambda is equal to the kernel of t minus lambda times the identity in V. Provided lambda is eigenvalue of t. So this is the so-called lambda eigenspace. Lambda eigenspace of V. On occasion, we won't actually use the value of lambda to label the e's. We might do like E1, E2, E3, E4, even though the eigenvalues are like the square root of 17, or the square root of 3 plus the square root of 352, and then 1 plus I, and then 3 minus 17i. See all those eigenvalues I just rattled off? They don't make good labels, right? But if the eigenvalue is simple enough, we might actually use the value itself as a label for the eigenspace. But you know, otherwise, maybe for lambda 1, we say E1 is, you know, the kernel of t minus lambda 1. All right. And by the way, I'm going to start using this shorthand because what I've been writing so far is a drag. Let it be understood that if I say an operator minus a number, what should that mean? What should t minus lambda 1 mean there? Yeah, that should be lambda 1 times, not the identity matrix, because we're not working on column vectors here, but an abstract vector space. But it should be like minus lambda 1 times the identity. I mean, it's this right here, guys, is just a shorthand for this, all right? Okay, fine. So that's what we're looking at. Let me give you just a couple of examples. Number one, if we have a vector space and we let t from v to v be 0 map. This is a very stupid map, right? T of v is equal to 0 for all v and v, right? So the 0 map has every single non-zero vector as an eigenvector with eigenvalue 0. So in this case, actually, E sub 0 would be equal to V, right? That's the kernel of T minus 0, aka kernel T. 2, keeping with my ridiculous examples, what if we look at the identity map on V to V, right? Then if we look at the identity map acting on, let's say, X for a change of pace, well, that's X again, right? Which, if you look carefully, you can see is 1 times X, right? So you can identify from that the eigenvalue is what for X? 1. Every non-zero vector is an eigenvector of the identity map with eigenvalue 1. So in this rather silly case, we have that E1 is V. Okay. Another, well, this isn't really very silly. This is another example, though. 3, we could look at the differentiation map, ddx, mapping from, let's say, smooth functions on the reals to smooth functions on the reals, right? If you're looking for an eigenvector, which we would in this context call an eigenfunction, what would you be looking for? You would be looking for ddx acting on some function y to be equal to lambda times some function y, right? In other words, what we're saying is that dy dx is equal to lambda y, which, if you've had differential equations, you would recognize the solution is y is equal to, e to the lambda x. This is, in fact, a solution to that differential equation. Because if you differentiate e to the lambda x, you get lambda e to lambda x, which is to say that it solves that differential equation. So what are the eigenvalues of the differentiation operator acting on smooth functions? I mean, my 0 map had eigenvalue 0. That was it. My identity map had eigenvalue 1. That was it. There were no other eigenvalues, right? How about this? What are the eigenvalues? By the way, the set of eigenvalues is typically called the spectrum of the operator because of the physical interpretation of eigenvalues as it relates to energy levels in quantum mechanics and spectroscopy. But anyway, what are the what lambda is allowed here? 1, 2, 3, 4, pi, square root of 2. Anything, right? So any real number is an eigenvalue of the differentiation operator, right? That's very different than examples 1 and 2. Okay. Here's another example, and this might be a homework problem, so my apologies if I'm working on your homework. How about this? We look at a linear transformation T from, say, n by n matrices to n by n matrices. Let me use something other than T, actually. Let's call this thing, I don't know, S. So let's define S by S of A is equal to A transpose, the transposition map. Think about this. What if we have a symmetric matrix? What is a symmetric? Symmetric A has what? A transpose equals to A, right? So that would give us S of A is equal to A transpose is equal to A. Apparently, we get eigenvalue 1. Right? So in this context, the eigenspace with eigenvalue 1 is what? I've called it Sn, right? Symmetric matrices. That's not great notation. I really need to come up with something better for it. Because past this point, you guys, Sn will be the symmetric group on n symbols, which means something rather different. And adding embarrassment to this, antisymmetric matrices, well, what are those? A transpose equals to minus A, right? So if we take S of an antisymmetric matrix, let me use B, just so you can see the difference. So if I take S of B, where B is antisymmetric, by definition B transpose, but antisymmetric gives us minus B. So what's the eigenvalue? I mean, it's an eigenvector, with eigenvalue what? Yeah, lambda equals minus 1. So eigenspace with eigenvalue minus 1 would be the antisymmetric matrices A sub n, set of antisymmetric matrices. And in fact, as we discussed last class, the direct sum of these gives us all matrices, right? So note, our n by n is equal to E1 direct sum with E minus 1. This is a special case of a more general theorem I want to share with you by the end of today. All right. So what's the spectrum for example 4? It's 1 and minus 1, right? The eigenvalues allowed are 1 and minus 1. And that's it, right? Are there any other eigenvalues? There can't be, right? Because the symmetric matrices and the antisymmetric matrices give you everything in n by n matrices. So if we had some other eigenvalue, that would contradict what we already have. Okay, I'm using theorems we haven't quite proved yet, but. So here's some examples to get us started anyway. So here's our proposition, 8.1.7. It says the following. For t, a linear transformation from v to v, in other words, an endomorphism, if there exists, excuse me, basis, beta for v, with the matrix of t with respect to beta, diagonal, all right. Well, let me restate the proposition this way. Get rid of that if. There exists a basis v for v in which, with is fine, but I'm going to write in which because I like it more, in which t beta beta is diagonal. If and only if there exists an eigenbasis, beta for t. I mean, so the reason I wrote this proposition in 2 sentences is because I struggled with the grammar. I couldn't figure out a way to write the sentence in such a way that it communicates that it's the same basis that does both of these things. All right. The basis which diagonalizes it is the basis which is an eigenbasis, and vice versa. Anyway, here's the proof. So suppose that beta, v1, v2, vn. Now, there is something else I should assume here that I have forgotten to say, which is kind of important. Assume the dimension of v is equal to n. Right. This is, okay, so like one of my examples, well, the first 3 examples are possibly infinite dimensional. I mean, 1 and 2, you could take v to be any dimension. These examples are reasonable. You could talk about the zero map on an infinite dimensional vector space, just the same as a finite. Well, there's one difference. It's harder to find the matrix for the infinite dimensional case, right? I mean, if you're Russian, you know these sorts of things, but most of the rest of us have trouble. So that was a compliment, not an insult. I have to make these things clear, because later anyway, I digress. This, on the other hand, is infinite dimensional, right? What's the basis for the set of smooth functions? It contains polynomials, right? That's an infinite set. On the other hand, example 4 was n squared dimensional. So example 4 would be in the realm of this proposition, all right? So finite dimensional vector space. Suppose beta v1 through vn is an eigenbasis. Excuse me. Gives t beta beta diagonal. What's that mean? Thus, there exists lambda 1, lambda 2, lambda n in F, right? Such that t beta beta is lambda 1, lambda 2, lambda n. That's what it means for it to be a diagonal, right? They could be repeated, but they have to be in the field. Diagonal, right? What's the meaning of that matrix as it relates to the basis? Do you guys remember? So like the first column is what? That's t of v1 with respect to the beta basis, right? T of vn with respect to the beta basis. AKA, we have that the coordinate vector of the jth vector in this basis with respect to the beta coordinate system is lambda sub j times ej, right? So each column in a diagonal matrix is the standard basis element times a number. That's what it means for it to be diagonal. But what does that mean? So we have the phi beta coordinate map, right? Acting on T of Vj is equal to lambda j ej. So what do? Just act by phi beta inverse. This says that tvj is phi beta inverse. How does phi beta inverse work? What did I tell you guys about the inverse coordinate map? What does it do? It's a machine that changes the standard basis back into the abstract basis that we're considering, right? We can pull the constant out, and so what we get is lambda j vj. See, because the inverse image under the coordinate map of Ej is Vj. But what does that say? By the way, is the V sub j non-zero? Can you have a basis that includes the zero vector? No, that would be linearly dependent, right? So what does this tell us? This says, therefore, Vj is eigenvector with eigenvalue lambda sub j. Consequently, beta is an eigenbasis, right? How about the other direction? I think if you're Chinese, the proof is already on the board. Because you can read right to left, right? So like the other direction, we assume that it's an eigenbasis, which gives us this, right? Which then implies that, which implies this, which implies this is equal to that, which is to say it's diagonal. So really the same calculation in reverse is the proof of the converse direction. So guys, if you want to diagonalize a linear transformation, what do you want to do? You want to find an eigenbasis, right? And if no eigenbasis could be found, then such a transformation would say to be would be, well, what's a good word? It would be not diagonalizable. I guess you could say undiagonalizable. I'm not sure that's actually something we say, though, now that I think about it. Say those words out loud. How about A? What would it mean for A to be diagonalizable? Definition, if we have A in Fn by n, then A diagonalizable means what? What that means is that there exists P invertible in n by n matrices such that P inverse AP is a diagonal matrix. By the way, we could also define eigenspace, right, for a matrix. How would you define the lambda eigenspace for a matrix A? So the eigenspace for matrix A, watch this. So just the same, but with the identity matrix, now we got the identity matrix, like that. And again, let it be understood for a matrix that if I say A minus lambda 1, that lambda 1 is now shorthand for lambda times the identity matrix. So we can also calculate eigenspace for a matrix. All right. There is an obvious and an almost silly interplay between the matrix and a linear transformation. And let me write that down for you guys, if I can find a spot. I Probably shouldn't have done that. Oh well. So this is proposition 8.1.10, and here's what it says. If we have an n by n matrix, right, and left multiplication L sub a of x is what? By definition, that's ax, right? For all x in Fn. And if we have T is a linear transformation from V to V with the dimension over f of V equals to n, then we have the following. Number one, x in Fn is eigenvector of A with eigenvalue lambda if and only if L sub A has x eigenvector with eigenvalue lambda. I'm sorry, I'm embarrassed I even wrote that on the board. That is so obvious and silly to spend class time to write it. Seems very silly on my part. But this is the interplay between, if you want a matrix, you want to turn it into a linear operator, you just look at multiplication by the matrix. That gives you the corresponding T, essentially, right? And likewise, V in V with T of V equal to lambda V. In other words, lambda is in the field, right? Eigenvalue for eigenvector V. That's going to be true if and only if what? For, and this is what's missing in the notes, for each basis. For each basis beta, we have that the matrix of T, beta beta times the coordinate vector of V is equal to lambda times the coordinate vector of V. In other words, you can find eigenvectors, right? You can find eigenvectors for a linear transformation by studying the matrix of that transformation with respect to any old basis. Right? So if we can learn how to find eigenvectors for a matrix, then that means we can correspondingly find the eigenvectors for the linear transformation because of the natural interplay between coordinate vectors and their abstract vectors that they correspond to. Okay. So let's see here. Given that, right? So looking back at the definition of A being diagonalizable, how would you actually diagonalize a given matrix, or at least try to? What would be the procedure for diagonalizing a matrix? How do you find that P? What is that P? Here's the procedure to diagonalize A. So step number one, find eigenbasis for L sub A, right? If you can. There's no guarantee that we can do that, by the way. But if you can, suppose you can, right? Say beta equal to V1, V2, Vn. This is a subset of Fn in this context, right? Step number two is you look at the matrix. What is the matrix of L sub A with respect to the beta basis? By our coordinate change discussion, that's the beta inverse matrix. Oh, wait a minute. Well, let me check my notes here in just a second. I'm worried about have I forgotten an inverse or something stupid? I don't think so, though. Yeah. So this is fine. What is the standard matrix of L sub A? What? I heard a still small a. A is correct. Yes, that is exactly A. So what we have here is A is the eigenbasis matrix inverse times A times beta, and that would be equal to what's, by construction, right, by the proposition we just went through, if we have an eigenbasis, it's diagonalized, right? And so this would be equal to lambda 1, lambda 2, lambda n, which I will sometimes refer to as just generically D, the diagonalized form of A. So that's how you do it. You want a diagonalized matrix? Just got to find the eigenbasis and go to town. He's like, well, that's great. Why do we care? Well, there's lots of reasons to care. Here's one. Uses. One application, or app, as we like to say these days. Suppose you want to calculate A squared. How would you calculate A squared? Well, let me invite you to thinking of A as actually being A is equal to beta D beta inverse, yeah? So see, A squared is really beta D beta inverse times beta D beta inverse. Sorry. You should know by now that if you sit there, that's going to happen. Yeah, I'm not trying to hit you. Sometimes I try to hit students there, but not you. So if it happens, it's an accident. Unless, of course, you just said something offensive, in which case I will take credit. But of course, beta inverse times beta is just the identity matrix, and see what happens is we get, what do we get? We get beta D squared beta inverse. By the way, that shows us that D squared is also equal to beta inverse A squared times beta. Also, I mean, that's interesting. So let me say star is interesting. Star star is also interesting. Star star is interesting because what is the square of a diagonal matrix? It's the square of the diagonals, right? It's lambda 1 squared, lambda 2 squared, lambda n squared. Yeah. Is it easy to square a diagonal matrix? Oh, yes. It's very easy. Is it easy to square an arbitrary matrix? Not so much, right? So you see that if we are willing to use this eigenbasis trick, we can easily square a matrix by simply squaring the diagonal matrix corresponding to A and then multiplying before and after by the appropriate change of basis matrix. But there's something else that this calculation shows us. It shows us that if A is diagonalizable, well, so is A squared. All right? Is there anything really special about looking at the power 2 here? I mean, is this also going to be true for like A cubed, A to the 4th, A to the k? In fact, it is, right? So this application just as well works on the kth power as it does for the square. So that's kind of pretty. All right. So there's a giant gaping hole in our thought process so far, and that is, I mean, if you've been paying close attention to what I've done so far, you'll notice that I have pulled the eigenvalues and the eigenvectors from the thin air, right? I mean, I basically Did I derive that the symmetric matrices and the antisymmetric matrices were eigenvectors for the transposition map? No. I just wrote those down as was familiar from our experience. So what if I do something like, you know, A equals to 1, 2, 3, 4, find eigenvectors? See, that question is, at the moment, completely outside our scope, right? So this theorem addresses that need, and it says something rather beautiful. So here it is. These are the equations characterizing the eigenvalues for A or T, right? So number A, if you have an n by n matrix, all right, then lambda in the field is eigenvalue for A if and only if the determinant of A minus lambda I is equal to 0. Likewise, if we have a linear transformation on a finite dimensional vector space, all right, then lambda is eigenvalue if and only if the determinant of T minus lambda is equal to 0. Where, of course, that is lambda times the identity map. By the way, these equations I just wrote are so important that they get a name. They are called the characteristic equation for A or T. So this, I'll box them in green. These are the so-called characteristic equations. Characteristic equation. So eigenvalues appear as solutions to the characteristic equation. How do we prove this? I'll focus on the matrix case, all right? Suppose you have an eigenvalue, right? In other words, suppose you have an eigenvector. What's that mean? If there exists v not equal to 0, such that A minus lambda times the identity times v, right, is equal to 0. What does that say? That says that the kernel, well, the null space of A minus lambda I is non-zero, right? Or if you like, you could notice that if I multiply A minus lambda I times the 0 vector, I get 0, right? So I've got non-zero V, and I've got the vector 0. Both of those mapping to 0 under this operator, under this matrix, A minus lambda I. That means that the inverse of that matrix does not exist. Because if it did, it should map 0 to 0 uniquely. And you could undo it by multiplying by the inverse, right? Therefore, A minus lambda I is a matrix which is not invertible, right? And what did we learn in the theory of determinants? We learned that that must mean that the determinant of A minus lambda I is equal to 0. Because if it was not equal to 0, then we could use the classical theory of the adjoint, or the adjugate, whatever you want to call it, to build the formula for the inverse, which we apparently cannot do. So it must be that the determinant of A minus lambda I is 0. Conversely, if the determinant is 0, that means that there exists a non-zero solution to the A minus lambda I times V equal to 0 problem, and that non-zero solution is an eigenvector with eigenvalue lambda. So nearly the same argument gives us the other direction here. All right? So it's the non-invertibility, meaning determinant 0, which is so incredibly useful here. Okay. Now there's another definition I should tell you. Which is the characteristic polynomial. What is the characteristic polynomial? So sometimes PA of x would be the determinant of A minus lambda times the identity matrix, or for transformation, PT of x would be the determinant of T minus lambda times the identity. Fine, I'll write it down. There you go. So these are the characteristic polynomial. For A or T respective, yeah? What order is the characteristic polynomial? Here, while we're waiting for the screen to warm up here, let me do an example. If we look at the matrix A is cosine theta, sine theta, minus sine theta, cosine theta, then the determinant of A minus lambda times the identity matrix would be the determinant of cosine theta minus lambda, sine theta minus sine theta, cosine theta minus lambda, which is lambda minus cosine theta squared plus sine squared theta. So this equal to 0 would be the characteristic equation. The characteristic polynomial here would be, let's see, if I leave theta as like a variable, PA of x would be x minus cosine theta quantity squared plus sine squared theta. So does this have a solution? If we're thinking about this being in 2 by 2 real matrix, right? If it's a 2 by 2 real matrix, the answer is no. There is no solution to this. Unless what? I mean, if theta was 0, we're in luck, right? So ignoring theta, an element of, say, integer multiples of pi, this is irreducible. It cannot be factored. There is no real 0. Correspondingly, there is no eigenvalue for this matrix, which makes total sense if you think about what it is. This is a rotation matrix, right? What's the condition for an eigenvector? It says that T of v is equal to lambda v. That says that you do the transformation, and what happens after the transformation's done? You've got a rescaling of your vector, right? It could either be in the same direction, right? It could either be in the same direction, right, or opposite the direction if the eigenvalue is negative. What's a rotation do if it's not by a multiple of pi? It takes your v and it rotates it, right? No matter which v you start with, it's never in the same direction, right? So it makes complete and total sense that this matrix has no eigenvalues over the reals. So this is an example of a matrix which is not diagonalizable. Rotation matrices are not diagonalizable. Unless, of course, there's stupid rotation like the identity transformation, or the go all the way back around, the flip it over the inversion one. So there are some theorems I should tell you. First of all, if we have the characteristic polynomial, it has at most n distinct zeros. That's because this characteristic polynomial, the answer to the question I asked you guys was that it's an nth order polynomial. because you're taking the determinant of an n by n matrix, which has n copies of x or n copies of lambda in it. And when you look at the formula for the determinant, you can at most multiply the entries, one at a time. There's never a repeat in the determinant formula, right? So if you think about that, that means the max order could be n. In fact, it is. The leading term in the characteristic polynomial, as I have set it up, is minus 1 to the n times x to the n. I will warn you, if you look at some other books, instead of having a minus lambda I, and instead of having t minus lambda, they do it the other way. They have lambda times the identity minus a, or lambda times the identity operator minus t. But I mean, you got a choice to make. So now here's another one. So at most n distinct zeros, what if we have a complex n by n matrix? Well, then allowing repeats, a has n eigenvalues. Why do I know that? An nth order polynomial equation over the complex numbers has n complex solutions possibly repeated. This is the fundamental theorem of algebra, right? But for real, that's a real polynomial, the example I wrote out over there. But, I mean, there is a complex solution to it, right? Cosine theta plus or minus I sine theta is the complex solution to that, all right? And so if we looked at my example over there as a complex matrix instead of a real matrix, it becomes diagonalizable. In fact, this matrix A that I looked at in that example is diagonalizable as a complex matrix. You can find complex eigenvectors and find a corresponding diagonalization with respect to complex vectors and numbers. All right. But anyway, more on that later. That's about 2 classes from now. Now here's an explicit and boring example. I'll let you read it. What I do here is I actually show you, here's a typical test question, 2 by 2 matrix, calculate the characteristic equation, find its eigenvalues, calculate the null space. The basis for the null space is eigenvectors here. And so I have 2 eigenspaces, the 0 eigenspace, the 4 eigenspace, and together they give me a basis for the whole space, which is to say that this matrix is diagonalizable. And then I show here how we can calculate the nth power of A using the trick I just showed you down here. It's covered up at the moment, all right? So that's a nice example. Some language, we say a polynomial is split over the field if you can factor it into linear factors, possibly repeated. So my example over here, this polynomial is not split over the reals because we cannot factor. It's irreducible. But if any polynomial is split over the complex numbers, that's a fundamental theorem of algebra essentially. So this proposition connects the meaning. It turns out that the constant coefficient of the characteristic polynomial is actually the product of your eigenvalues, supposing you got them. Here's a 3 by 3 example. This one's kind of interesting. We have an eigenvalue of 4 repeated twice. That means it has an algebraic multiplicity of 2. The number of times the linear factor appears in the characteristic polynomial is called the algebraic multiplicity. So this has an algebraic multiplicity of 1. The geometric multiplicity, in contrast, is the dimension of the eigenspace. So we do the calculation for the null space of A minus 4i, and it actually is 2-dimensional. So in this case, the geometric multiplicity of eigenvalue 4 is also 2. The algebraic multiplicity is equal to the geometric multiplicity. That is tantamount to saying that this matrix is diagonalizable. And in fact, this, and this put together give us an eigenbasis, which diagonalizes this matrix. Here's the definition of algebraic and geometric multiplicity again. Algebraic is the number of times that the linear factor appears in the characteristic polynomial. The geometric multiplicity is the dimension of the corresponding eigenspace. These don't have to be equal. And when they're not equal, that is proof positive that your matrix is not diagonalizable. If the geometric multiplicity is less than the algebraic multiplicity, then that means you're missing eigenvectors. This proof right here shows that, in fact, the geometric multiplicity can be at most the algebraic multiplicity. They can be at most equal. It's possible that the dimension of the eigenspace is smaller than the algebraic multiplicity. That's what this proves. This is a complex example, another example. And then finally, the theorem I was going to share with you today. Well, I have a result here on linear. I mean, I'll tell you what this theorem says in a nutshell. It says that if you got distinct eigenvalues, eigenvectors corresponding to distinct eigenvalues, guess what? Linearly independent. So if you find me an eigenvector with eigenvalue 2, and I find you an eigenvector with eigenvalue 3, those are linearly independent vectors. But I prove it for k values here. And then finally, here's the theorem I wanted to make sure I at least said today. This is the big idea. If we have a linear transformation on n-dimensional vector space V over F, then the following are equivalent. T is diagonalizable. V is a direct sum of eigenspaces with distinct eigenvalues. For lambda 1 through lambda s, the V is the direct sum of these eigenspaces, right? If you have a characteristic polynomial is split, and for each distinct eigenvalue, the algebraic and geometric multiplicities are equal. So this is to say that it's split, and this is to insist that the number of times it's repeated here matches the dimension of the corresponding eigenspace. So that's what it means to have a diagonalizable T. So next class, I will continue this discussion, and I will talk about what happens when it's not diagonalizable, how we deal with that, and that brings us to what's called the Jordan form. So thanks, guys.